Hi everyone, welcome to the Deep Learning for Natural Language Processing course. And today's agenda is about word vectors and all the topics related with that. So we'll talk about lexical semantics, word embeddings, word2vec, glove, and then some NLP tasks and evaluation. More specifically, we'll talk about word sense ambiguation, also document classification, and multi-sense word sense ambiguation, per se. Okay, to start with lexical semantics, so far we have been looking into ways how we can identify words happening in a corpus, and we see, okay, is this the presence enough? We smooth that, and it's more about the word itself. We're kind of not having a grasp that deeply on about the meaning of a word or how they relate among them. And you'd be surprised, I would say that trying to find relationship between words with machine translation, it's probably one of the oldest challenges in natural language processing. There are some really good attempts how to solve that and even to use as a proxy. We'll go over a couple of most popular ones. And hopefully you remember this from the very first lecture that we skimmed over quite quickly. And if I say to you, and just to illustrate how semantics is not that trivial, if I say this club is great, what exactly do I mean by the word club? I'm talking about music or disc club or bike club or golf club or music club or whatever. And if for us to agree on how many meanings or how many definitions a specific word or specific construction has, imagine for you to code that. Is most certainly not trivial. And you'll see that most of the approaches that we'll start seeing from now on, they're kind of distance themselves from a more hard-coded approach on how to calculate, okay, this word here appears and that's enough for me to know its meaning, and we're going to move more to what is the relationship, how this first word connects to the second, or how much window that I consider a set of words is relevant when I'm calculating the probability of this happening in a specific corpus. Yeah, so I guess the first thing that we have to keep in mind is what is meaning, right? It can be an idea that's represented by a word, a phrase, or an idea that a person wants to express by using signs, or an idea that is expressed in a work of writing, art, and so on and so forth. There is a couple of different definitions for meaning, at least on linguistics and /NLP. The one that kind of most happened to work for us is simply the relationship between a symbol and this idea or a signifier and the signified object, in a way that meaning is simply the relationship that we have between those two things. And we'll try to explore this relationship as much as we can. And this is what we call the notational semantics. This is not the only way for us to illustrate semantics. There's a couple of different ones. So there is the compositional semantics, in which the components, we break down words into specific elements. And then we have ontological semantics, which how the meaning of a word relates to the meaning of all the words. Think as more as a graph / encyclopedia taxonomy way of dealing with words, and we'll see a couple of examples. And then we also have distributional semantics. And at least for non-low resource language, I would say distributional semantics is the way to go. This is what's happening the last easily 10 years. And it pretty much changed the idea on NLP for good. Before they were doing things in a specific way, and after the idea of using the distribution of words to represent meaning, it simply changed completely how we do an NLP. It's quite intuitive, but we'll get there. So the first one, the compositional semantics, in which we break down a specific concept into smaller concepts, and we try to use this to illustrate a specific meaning. For example, we have the word cake, and we say, okay, what is a cake? It's something made of, is a set or is a tuple or whatever elements composed of eggs, oil, milk, flour, and if I think about pizza, I'm talking about flour, salt, water, eggs, and so on and so on, so on and so forth. Do you see a problem with this kind of representation? It might be quite useful though. Yep.
If you have to define that for every word, it could be problematic.
Exactly. It's an endless job, right? If you have to define this, it simply does not scale. Not only that, how do you know when to stop? Because you can break down flour in smaller elements, and then you can break these elements in smaller elements. And is the order important? Is the occurrence important? And what that means for us? Also, who does this job? Is this the same concept across, let's say, different groups or different tasks? So how you would compare these things? So it's really, really hard. For this and many, many other reasons, this is not that popular in, let's say, computer science approaches. Maybe some other areas they use this to define what is an object and stuff like this. If you have to transpose this into whatever task or system that you have, that's probably not the best approach, okay? But still, it's quite useful to understand how they go. And then we have ontological semantics, or lexical database, or lexical taxonomies, or semantic taxonomies. There's a bunch of different ways for this, in which we organize the words and word senses or word meanings into a specific, either hierarchical architecture or kind of a distributed graph of knowledge graph. So before we see some examples about it, can you also see some problems about having this kind of representation in which you require that relationships between words and their meanings, they're somehow tied into either encyclopedic form or into a hierarchical form? It seems like a really neat idea. Like, let's organize knowledge and just link them and use them.
Lexical databases, do we have the strength of relations between the words?
Depending on the lexical database that you have, yes, they use something called, let's say, most used sense. So what they do is when they have many meanings for a specific word, the words that are indexed first, they have, let's say, the most used sense for that particular word. So it means that for every first word that you have, they're somehow more related. But this is not true for every single word, but it's a good point.
If it does not match, then we won't be able to identify.
That's a good example. When you're doing with inflection of words, not that trivial to account for every single variation that you have. And most of these databases, they're fixed in whatever word they have indexed there. Another problem with this, and I would say this is a problem on ontologies in general, not to criticize ontologies, but it's always like this. There are 100 ontologies for whatever problem or whatever definition. And then someone says, hey, I have a new ontology to describe this better. And this is the absolute to-go ontology. Now you have 101 ontologies. And this keeps growing because everyone thinks their definition, their organization is the one to use, is the one to go. Not to mention, it's extremely expensive to take care of this. It's not like you can do this out of nowhere. We'll see some of those lexical databases, and I'm criticizing here, not like don't use them. No, use it. They're extremely useful. But just take care, all right? Well, yeah, as I was saying, it's impossible to keep up to date. It's for sure subjective, and everyone has their own truth, of course. And not to mention that depending how granular you go, it might be either too much or too little for whatever you need to use. And we'll see some examples. So lexical databases, as we were saying, is whatever, it's some structures that organize the content, the word, the relationship between words in some specific relationship. I don't like to use that much the word hierarchy. I think relationship is better to describe this. We'll see 3 of them: WordNet, BabelNet, and ConceptNet. This is not an extensive list. There are many, many others. Some of them, if I'm not wrong, Microsoft Concept Graph, I think, was discontinued. But in any case, there's a bunch of them there. So let's see them one by one. Yeah, this is probably important. Now that we criticize how good those things are, you would be surprised how many techniques used this in the past, and they are still used to refine more up-to-date models. So you would see people using lexical database for word sense ambiguation, semantic evaluation, sentiment analysis, text classification, chatbots, question and answering system in which they have a specific language model, and then they use a knowledge database to check or to refine their answers, text generation, and so on. And not only that, they're a great resource for you to use with word embeddings. So how you code some specific word distribution that you have in your corpus. Since people spend a lot of time doing these lexical databases or these ontologies, why not to use this to have a specialized language model or to specialize word embeddings with knowledge that you already have? So this is quite neat. The first one we'll talk about is WordNet. It was the largest lexical database for English words. Now I guess BabelNet is bigger, I would say, but in any case, good thing about WordNet is fully integrated with Natural Language Toolkit, so there is no hustle in order to use API or its senses. It's ready to go. The knowledge and the words and the relationships, they are all specified as synsets or set of synonyms. So every word has a specific general concept, and on that node, they are related with specific attributes, and we'll see some of them in a minute. It was created in Princeton University by Professor Miller right here, and now at least the English version, or they also call this Princeton WordNet or just English WordNet, is Professor Feldbaum is taking care of this version right now. The English WordNet is definitely not the only one. They have way more than 70. I think right now they are 80, I think, or 90. Not all of them, they're open source, so it's not like you can use every single resource for this language. Some people maintain this in a restricted access, but you can most certainly apply to use that if you have affiliation with the university. Also, they have their own conferences, their association. It's quite a nice group to work with. So what information is attached to every single word or synset that we have there in WordNet? So for every word that we have here, the main element of this word is a synset. And for that synset, we have around 23 attributes. Not all of them are specifically meaningful. Some of them, they are artificial relationships simply to help organize their structure a bit better. But some of them, I would say more than half of them, they do have a purpose and a meaning. For example, associated with the word, you have hypernym, meronym, gloss, which is an example, the domain of that use, the part of speech. Some of them, well, most of them, they have an example how to use their lemma and so on and so forth. And how does it look like for us? So the WordNet structure that we have, if you access, pretty much, let's say we work for the word, we look for the word Java. When you do this, you're going to receive 3 synsets. In this case, synset is the entire, let's say, this entire string that we have for us, and each of those things here, they have a meaning. The first one here is the lemma name, so it's the word itself associated with the synset. Then the part of speech it has, and then the meaning that you have for that specific lemma. Then you have offset, a part of speech, a gloss. This gloss right here is an example sentence in which this would be used. So in this case, an island in Indonesia to the south of Borneo, one of the world's most densely populated region. You already have the kind of a definition for that. Not only that, all these glosses, theoretically, and at least in the beginning on WordNet, they were composed by linguists and psychologists. So it's an extremely granular and curated database. Not only that, I mean, think about how resourceful is to have this definition. So you can explore quite some neat alternatives, how to work with these attributes. In the end of the class, hopefully we'll be able to see a couple of them. An example, not every single scene set has an example. In this case right here, this first one has none, and then this scene set for coffee, which is part of this scene set right here, has he ordered a cup of coffee, and so on. There's offset. This is quite important, I would say. Offset is an integer that uniquely identifies a specific scene set. So sometimes some scene sets, they might overlap, or they might have an overlapping gloss, or they might have the relationship might also overlap. And what they do is they create this offset. So you can, if you have a part of speech, the sense and also the offset, you can uniquely identify every single scene set that you have in this structure, which is quite neat. Another set of attributes that I didn't put it right here is one of those soft characteristics that I mentioned. They also have something called related scene sets, in which is not a rule how you simply relate one scene set to another, but they come up to a consensus that, let's say, football and ball, they are somehow related, so they put in this list. Needless to say, it's quite hard to find a rule for that, simply because it's really subjectively done by them, okay? On some of the relationships that we have there, we have synonym, which is pretty much equivalence, like small and little, antonymy, small and large, hyponym and hypernym, and this was even used a couple of years ago to calculate how close specific meanings are one from another, and this is pretty cool. What is the idea of hyponym and hypernym? One is about a more specific meaning, and one is a more general one. So on the hyponym there, I said hyponym, sorry. Hyponym, it means that I'm talking about more specific concept. For example, a dog is a kind of, or is a mammal. And hypernym is the other way around. So mammal is more general to a dog. And they use this kind of this hierarchical chain also to see how far those meanings are one to another, and they are able to quantify this distance and use this to have a new measure for similarity, not just using a cosine similarity as we saw in the last class, okay? And that's there's an extensive list of all these relationships. Some of them, they are completely artificial and they don't mean a thing. They put it there simply because it makes it easier to connect the meanings. Yes?
That's not like you can't see it in this example, but what's the reason to store it this way? I mean, there's some reason why both are stored.
What do you mean? How the hierarchy? Because this it's like a
Yeah, you
pointer.
said really difficult. Like there's dog and melon and dog, and it's the same. Just the other variation. Like the hyper.
Mm-hmm.
And just my question was like, why doesn't one of them suffice? Like there must be another example where there is a reason why you store both of them.
Yes, and in fact, it's like every scene set, they have these attributes that we just saw right here. They will have another line saying, okay, this is a hypernym or this is a hyponym. So some particular words, you are able to track it down specifically from, let's say, the most specific word to a more general one. Nouns, you can do this. For example, I think the first three are organism, concrete being, and abstract being. And then from this, you derive until it's more specific. And some of them, they don't have this more general or more specific relationship, so you don't keep track for all of them. And not every single category of word, they will have this relationship. For example, verbs. You cannot say, let's say, love and running, loving and running. There is no hyponym and hypernym relationship between this. So all these attributes, they are not present for every single scene set, so you don't store all of them, just those that they judged to be some sort of hierarchy. This is most true for nouns. Actually, this gets us to a specific point. If you're working with nouns, WordNet is great. Verbs, kind of-ish. Adjectives, yeah, and then adverbs just go down the sink. So it depends on which kind of word you're working on, okay? Okay, BabelNet. BabelNet, think as in short, is a WordNet on steroids. It has almost everything that WordNet has. It's a bit iffy. We'll talk about some of the problems and limitations at the end. But think as a multilingual encyclopedic dictionary in which every time it's exactly like this. Like every time you have a word, you have a bunch of different encyclopedia information about that specific word. Not only the language that you search, but all the other language that they also have in their system. And it was created by Roberto Navigli in 2012. I wonder the date. I didn't mention this before, but Professor Miller, he passed away in 2012. And BabelNet was published in 2012. And they use WordNet as a resource. I wonder why, but be that as it may. Any case. And they also bring this kind of knowledge from other sources. Not only they have the meaning of every single word in their database, of course, but they also relate that with other knowledge databases in which they can provide more resources about. For example, given a term, they will present results from Wikipedia, Wikidata. Of course, they condense this into a nice user interface, and they will show definitions, or if it's specific about a company that you're looking, they have a database from Microsoft that helps to categorize this better. They have a geo names in which makes their geolocation words related way better also. It's really, really useful resource. There are some problems with this. I'll talk about the end when we compare all the lexical databases. All of them, by the way, all of them have problems. There is not a single one that, hey, this here you can use for everything you want. You will look for which database you can use for whatever task you have, okay? And then we have ConceptNet. I like the definition from ConceptNet from Robin Speer, and she created this at the Media Lab at MIT in 1999. ConceptNet is a knowledge graph of things people know and computers should also know, expressed in various natural languages, and is as loose, its structure, in my opinion, is as loose as its definition. It's a totally distributed graph in which things relate to another and as sparse as it sounds, which is both good and bad because you don't have kind of this hierarchy between concepts. It's more spread out, but also this is a drawback because it's hard for you to keep track how things, let's say, are, inside one from another concept. But in any case, it's freely available semantic network designed to help computers understand the meanings of words that people use. In theory, in practice, is not that nicely, I would say. And what are the elements that ConceptNet has? ConceptNet was really popular a couple of years ago. Now, I recently looked in their repository again. Some of them are not updated for a couple of years. So the way they define is, ConceptNet is a semantic network, is a knowledge graph, is used for natural language understanding, and they have all these relationships. For example, what is ConceptNet composed of? Crowdsourced knowledge, lexicography, games with purpose, linked data, and so on. And all of these blue ones right here, if you go in their repository, they have some sort of extra resources associated. Some of them are already not working. I think the knowledge graph is not updated for a long time now, but the word embeddings one is still quite used, I would say. And yes. Okay, about our data sets. Lexical database, sorry. We have WordNet, BabelNet, ConceptNet, and so on and so forth. So what is the bad side of them? WordNet, for example, has a large number of senses for every single word. And yes, that's good, kind of-ish. For example, I think animal, they have around 15 scene sets associated. Some of them people simply don't use it. So it makes quite redundant to use this information, especially if you have to traverse this entire thing. It's quite troublesome. WordNet can be too sparse or too granular for some applications. If some concepts, they are really specified in a way that they're really specific, like you will find, for example, the words, I don't know, perseverance in WordNet, and you find a specific definition for that. If you want something more general, you might not be able to find. Depending on the task that you have, of course, you might not find your concept there at all, which is also troublesome. ConceptNet does not assume that words fall into sync sets, so it makes it quite hard to group them in some sort of a logic structure, simply because since the components are loosely related, there is no hierarchy for you to explore. This happened also for verbs and WordNet. They have no explicit relationships aside from the related sync sets that most of times is also empty. BabelNet have a representation of WordNet style. So all the words there, they are categorized into word senses or sync sets. There is also DBpedia. DBpedia is more focused on named entities. A good thing on WordNet, it is integrated with Natural Language Toolkit. BabelNet has its own API as well with ConceptNet. ConceptNet, I didn't put it here, but they have their own pre-trained word embeddings, which makes life way easier. You don't have to calculate them from scratch. So imagine that they already have a list of vectors and words. It's a dense representation, so every word has a vector with 300 dimensions, so you can use it. So if you don't have to, nowadays this is not that much problematic, but imagine doing this in a computer from 99. It's quite troublesome, but now I guess everyone would be able to run this in their machines. This here, and at least the last time I checked, and I forgot to update right here, do you remember all the resources that BabelNet was using? Wikidata, Wikipedia, DBpedia, WordNet, which is open source, by the way. BabelNet, as for 2000, I would say even 2020, I looked into this, is not entirely free for you to use. You have some tokens that you can query every single span of time. I think it's days or week. It's 1,000 whatever coin they have there. And after that, you cannot access the data anymore. However, they say that if you're using for educational purpose, you're free to use, you're free to download its index, and it's fine. However, again, you need to be affiliated with the university. It doesn't mean that if you just say, yeah, I want to use this because I want to study or something, if you don't have a university email, and at least the last time my PhD student tried to use that, they were not, you would only be able to access this if you are registered as a PhD student. Maybe they made this a little bit loose, or depending if you're part of a project, they will make this available, but it's not as transparent as it sounds. So just take care using this. But it's a great resource anyway. And Microsoft Concept Graph is a proprietary taxonomy of English nouns connected with is-a relationship. And I'm almost sure that they just discontinued this, or was the academic concept graph. There is one specific lexical database that they don't use anymore. It was turned off a couple of years ago, but in any case. These are just a compilation of some of the limitations those have. Of course, they have way more. That being said, I think we can already start moving to something a bit more close to what we'll be doing for the next lectures. Remember, we talked about the compositional semantics, ontological or lexical databases, and now we're talking about distribution semantics, which is pretty much the idea that a word meaning is given by the words that frequently appear close by. And people, especially when they start talking about word-to-vec or word embeddings or dense word representations, they usually like to use this sentence right here that, yeah, this is from Professor Firth, and you shall know a word by the company it keeps. Although it's completely true, it does happen not only in words, I would say. You can even extend this to social situations. this concept is a bit, is an update version from this from 54, in which Professor Harris said, if A and B have almost identical environments, we say that they are synonyms. And this is for sure happening in NLP, and this is explored a lot nowadays. As I was saying before, this is one of the most successful ideas in modern NLP, and we can use a simple example to show that. Let's say, what is, again, word distribution semantics. When a word W appears in a text, its context is a set of words that appear nearby, either in an indefinite window or in a very specific limited one. For this example, let's say we have these 3 sentences. Then you can take your time to read. Our trip to Java last summer was amazing. I'm used to Java now. There is not a strong reason to change. 1 cup of Java, dark roast, please. We don't have anything mapped to that, right? But you can still infer the meaning of that simply by looking around and seeing how the things, the words that accompany that center word right here. And you can use this example for many other words like banking and so on. So the idea that we'll see with distribution semantics from now on is every time we are interested in representing one word, we'll look around to define the meaning of that center word, or the other way around depending on the algorithm that you're using. Okay? That being said, let's move on to actual word embeddings, the topic of the lecture. So, so far, we have seen how to represent words and words context, how we do this. We already saw some approaches how to do that, especially on the sparse vector representation. On sparse vector representation, we have bag of words, TF-IDF, anagrams, smoothing, and all the techniques that we've seen so far. Presence, frequency, absolute counting, discounting, and so on. Those techniques, they do have not only the sparsity problem, the vocabulary problem, but they also have the number of features that they're using. It doesn't matter if you're smoothing them or either by discounting or add one or whatever. In the end, you're going to end up with a lot of features. And what we mean a lot, the size of your vocabulary. And this is extremely troublesome to deal with, especially, let's say, if you're using SVM or something, any other machine learning algorithm. This gets really hard to compute, and you want to avoid the situation. Instead, from now on, we're going to move on to a dense vector representation, and all these algorithms here, I think we are not talking about universalness encoder, but in any case, we'll talk about word-to-vec, GLOV, paragraph vectors, or also known as doc-to-vec. Maybe we'll go very quick over this. And then FastText, Elmo, BERT, and so on, all of them they use, and all their variations they use dense vector representation, okay? So just a quick recap, how we compare those 2 kinds of representation. The first one is a high-dimensional vector representation. We have more features, and yes, if you don't deal, you will have a lot of zeros as well. And on the dense vector representation, we are more talking about low dimensionality. And what is low dimensionality? It depends on what time you're talking. If you talk between 2013 until, I don't know, 2016, 17, is between 50 and 800, 700, 1,000 dimensions. Now we have something like 2,000, 4,000, it really depends. Also, they do generalize better than explicit counts. It kind of follows in the same category when we were smoothing things before, and which is quite interesting. And they almost have no zeros, which is nice. This is more just a recap that we had. So we're moving from a term document matrix in which we have specific words and counts, and how we would use this vector representation. In this case, we have apricot, digital, and information. And if we were to calculate the similarity of them, we do the cosine similarity right here, and we use the dimensions, whatever these dimensions are. In this case right here, we have a dimension that's large, data, and stuff. We can have whatever, like count, part of speech, it doesn't matter. And then we'll calculate the similarity. So between apricot and information, we have a similarity of 0.16. Digital and information, of course, considering the features that we have right here, it's a higher similarity. And when the documents, they don't have any overlap features, or their overlapping features, somehow they're zero, in this case right here, we'll see that when we do the dot product, they're not similar at all. In this sparse representation, we see that every time we are comparing things, it's kind of a hard cut. We don't have things smooth out, which make things a bit complicated, but we'll get away from this. So in that representation, we already talked about these problems, the curse of dimensionality, the dot sparsity, and also, we didn't mention this that much, but it does ignore the context. It doesn't matter how far or how close they're happening in our text. Early approaches for dense word embeddings, they do take the context into account, but not in the sense of distance in the context. So later on, we'll see some techniques that they try to estimate a center probability looking for the words around. It doesn't matter how far you are within this window. As long as you are in this window, you calculate the probability the same way. So, but other approaches later on, we'll see that the closer you are to the center word or the reference word, you mean that you will see that you will be more accurate, or let's say you can give more importance to this. Yep.
What do you actually mean by
A center word, for example, if you have, let's say, a sentence and you have a specific window that you consider a certain number of words, and then from this number of words, let's say 5 words, and then you want to calculate what is the probability of one center word looking to its immediate context. So assuming that you have a window of 5, you will be looking to the 2 words ahead and the 2 words behind. In this window, the idea is you slide this over against the entire corpus, and then you're always calculating, I'm jumping a little bit ahead, but we are calculating 2 kind of probability. When this word that you were considering is the center, and when you move this sliding window, this word will be the context. So you will have 2 vector representations for this word. So this is pretty much, okay? Well, going to this direction, one natural question would be, okay, why do we want to use dense vector representations? To begin with, short vectors might be easier to use as feature in machine learning. So imagine that we're going from an input sequence of, I don't know, 10,000, 100,000 dimensions to something as 300. And you would be surprised how well even vectors of the size of 50 or 100, they actually do the job pretty well. Of course, we're talking about an era before 2017. After 2017, things change, but we'll get there, all right? They do generalize better than storing explicit counts, and we already saw that a dense representation, even using the count and the smoothing, they were somehow better representing the data that we have. So things were not so like 100% or 0. They were more distributed, and the idea is for us to use this nuance. Not to mention, if we have words that are written with a different lemma and they do have the same context, if you have enough example, you can approximate the vector representation for words that are written differently according to their context. And what do I mean by that? Let's say you have car and automobile. They are completely different words, written differently. They mean the same, but then how do you account for all their variations? You don't. You do this in an unsupervised manner, and if they occur hopefully in the same context, their vector representation will be the same, and you can explore that. For example, let's try to extrapolate. Think about machine translation. Let's say when we try to translate between French and English or German and English, you have enough examples, so you can work with this, let's say, natural alignment pretty easy. Now, transpose this to language where it's hard for you to do a translation. If you're able to code, let's say, the context on these words and where they occur, you have a natural alignment between different languages automatically. And this actually was a project, I think was 2000, 16, or it was in the verge between 16 and 17 by Google, in which they analyzed the content from Wikipedia from different languages, and without doing any translation or whatsoever, they were able to align the vectors between Portuguese, was Korean, Japanese, and another language. And this is pretty neat because you can improve your translation systems by using this natural alignment that they have, which is pretty neat. Okay, yes, still on dense vector representation, you might be thinking, yes, let's go to Word2Vec because Word2Vec is dense vector representation. Just calm a bit. Word2Vec is not the only way to obtain dense vectors. It's another approach of doing this. You can also have this with simple TF-IDF if you account for the top X words and then you normalize, smooth, and everything. You also have a dense vector representation. We have some of this approach to do this. You can do single value decomposition, a neural language model in which Word2Vec was actually inspired. And most of the approaches that we'll be seeing here, they fall in this category. We'll get there. And broad clustering that works with bigram hierarchical clustering. We are not covering this in this lecture. Okay. On single value decomposition, what is the idea? We approximate any dimensional data set using fewer dimensions. Which fewer dimensions? The one that means the most for us. And I can go pretty quickly over this. Pretty much you take whatever matrix of term representation that you have, you decompose in 3 of them, in which you have single values, left singular values on the diagonal, and then right singular values. And then on this mid matrix that you have right here, you can cut off to use, let's say, the first portion or the highest value that you already have in your corpus. But we're not going to this direction. Probably you see this in linear algebra here or something, hopefully. We're not exploring this, by the way. More on what we're going to do from now on is we're going to explore how we can use neural networks to kind of represent all those words that we have in the relationship between those words. And the idea is to, in this case, for example, that we have just one hidden layer right here, we're going to have a specific set of inputs, and what's going to be this input for us? It's going to be simply the representation of those words. How you represent them? Well, you can either start their values in whatever vector representation randomly, or you can start with whatever counting. It's not very effective. People don't do this. Or I still wonder if people are still using this today. We can use word embedding algorithms in which we'll talk about to initialize your neural network. So you don't start with random values, but you build on top of some previous calculated distribution for those words, and then you start refining this representation with your architecture. And then we'll see how we can scale this. And by the way, I'm jumping at least 2 or 3 classes from now on, how we can have more layers and have this working out for us. Let's see. Okay. The first algorithm that we'll talk about is Word2Vec. And for that reason, I will stop the recording right here. So, as we were talking before, we were moving away from a sparse vector representation to more dense vector representation. Still, we're going to be talking about static word embeddings. Later on, we see that on top of a dense representation, we can have contextual word embeddings. As for right now, every representation that we will treat, it's still static, and I mean that after you calculate that, there's no way, or let me rephrase that, there's no direct way to change the weights or the vector representation for those words. There are some techniques that allow you to do some further training or some adjustment in those vectors, but it's not that direct. Later techniques, after 2018, 19, you see that it's done kind of automatically for you. Okay? And that being said, I would say one of the most fundamental contributions that we have in the area is Word2Vec. It was published around 2013. I don't remember exactly when the preprint was available, and the title was Distributed Representation of words and phrases and their compositionality. There is also another paper on the same direction, Mikolov, which is the first one here on the left, top left, and his collaborators. They published that, and don't get we'll get on the actual contribution, but don't think like, hey, 2013 they had this great idea and that's it. Although the work was published in 13, he was already working this since 2007 and 8 in his master thesis. So after we're working a lot, this got some traction. And what is the idea? We're going to use a large amount of text or a collection of text, and then for every word in a fixed vocabulary, we're going to represent this word as a vector. In fact, there are two vectors we're going to use when this word is a center word in our window or when this word is a context. Later on, we average those two vector representations, and then we come up with this let's say, dense continuous value in a low dimensionality space. And then we do this for every single position in this corpus that you have, and hopefully by working out with the observed probability that you have and the one that you calculate, hopefully this will be able to extract and represent some meaning for you. And then, again, we go through each position T in the text, which has a center word C and context or outside the word O, and we'll work out how we can actually derive these probabilities and use them to represent our words, okay? And then the idea is, and all this, let's say, this vector representation, in the beginning, they are randomly initialized. There are some side notes on how they actually come up with those values, but by adjusting these values on and on based on what you were observing, hopefully this will be a good approximation. You will never get to the actual probability because there is no way to do this. You don't have enough text, and the adjustments, they just try to minimize the difference pretty much on what you're having there and what you calculated, what your prediction is, okay? And as I was saying, I mean, they published this in 2013. They were already working on this since 2008, but this dates back a little bit before with the work from Yeshua Bengio and then later on from Colbert, in which they were already using some running text or free text as an implicit supervised training data to have their dense vector representation in lower dimensionality. Later on, we'll see pretty much how they did that using recurrent neural networks. But the idea is pretty much to use the text and the co-occurrences or the co-occurrence within a certain window and use that to represent the word that we have. Yes, and this work from Benji was published in 2003, and he got the Turing Award, which, for those that do not know, it's kind of the Nobel Prize in computer science. So he got that in 2019. And if I'm not wrong, Colbert, he got the Time Award, the Paper Time Award in 2018 in ACL or NACL, I don't remember. But these are all, let's say, really influential people in the area. And what we'll be doing now to calculate the probability and the words that we have in our running text and later on use the representation. The idea is we're going to have a center word position, let's say T, and then we'll try to, let's say, we'll try to calculate what is the probability of a context word given that we have this center word right here. And this window size, it's pretty much a free parameter. You can define how far you want to consider your context. Theoretically, the larger is your window, the larger is your context, more accurate will be the co-occurrence of those words, simply because you have more information embedded in that window. There is another version of this, we'll talk later, but the two, just jumping a little bit ahead, either you calculate the word in the context based on the center word, or you do the other way around. And these are two different algorithms, and they have their, let's say, advantages and disadvantages, but pretty much those two algorithms were proposed. And then we move the center word according to our text over and over until we pass through the entire text in a hope that by calculating these probabilities in this window and they making the adjustment accordingly, we'll be able to have a better representation. So Before, into was our center word, now is our context word because we are considered banking our center word. And you keep doing this over and over again until you finish your entire corpus. Okay, and now let's dive into a bit more on the specifics, what we are actually trying to accomplish. So for each position T, from the very first word and until the end of your vocabulary, or the end of your corpus, we're going to predict the context words within a window of fixed size M, given a center word WJ right here. So we're pretty much calculating the probability of having this word here, the context word, giving the text within a specific window. And we do this, of course, for the entire vocabulary. And how we pretty much define this, we define as a likelihood L of theta here, and theta represent all the variables that we have to adjust, that we have to optimize. And what that means, imagine that we have vectors to represent all those words, and in our simple scenario right here, those vectors, they have values and from, I don't know, from 50 to 1,000 dimensions, and each iteration that we have in this process, we will start adjusting those numbers. And this theta is to represent all those variables. There are other free, let's say, free parameters that we can also wiggle around. Later, we'll show some optimizations to this specific part, okay? The thing is, we already talked about this, working with a product of probability is a bit troublesome. There's underflow, we don't do well with multiplication, and so on. It's easy if we simply transfer this to the sum of the log probabilities, which pretty much embed the same meaning for us. So the idea is we're going to have an object function called J, and then we're going to minimize the average of the sum of the log probabilities of the same parameters that we have before. And if we minimize this function right here in the bottom, we're pretty much maximizing the likelihood of between the context words and the center words. Okay? Before we actually go into how we can derive this to identify where these adjustments they have to be done, we do have to go some details first. So we do want to minimize this objective function right here, and how we calculate what are the parameters that we are actually considering. We will change some of the notations, and during the course we will change some notations also to make our life a bit easier. So instead of writing this here, we're going to give some specific names. So to calculate the context word and the center word, we use two vectors per word that we consider. When V of W, when W is a center word, and U of W, when W is a context word. And again, in the end, you do have two vectors, but then you average them to have one single vector for a word. It's pretty much when you, I don't know how many of you already play with word2vec, when you say, we do that mathematical operation, king, man, and queen, pretty much is an average of the context representation of that word and the center word representation that you had, okay? Yeah, I should say this. And how we do this, to calculate the probability of our context word, given that we have our center word, we're going to do the dot product between those two vectors, and we're going to divide this by the sum of the entire, let's say, vocabulary that we have there, and this will give us a probability distribution of all the words that we have in our vocabulary. For those already more familiar with this, oh, but this is really not efficient. Yes, that's true. But to teach the idea of that, this will serve our purposes, all right? And later on, we will present some optimizations that we have in this algorithm, and even some techniques that were proposed on top of that that make things a bit better. But if you understand pretty much the motivation on this, let's say, fundamental block, later on things will go smooth, in my opinion, all right? So when we are saying that we're calculating what is the probability of, for example, word turning, what's this context, given the center word banking, we're kind of giving a short, let's say, a short naming for all the parameters that we have there, which is the final vector for the word turning, the word banking, when turn is the context word, when bank is the center word, and all the other parameters that we have. We won't be writing all of this all the time simply because there's limited space, all right? And again, we're going to be going over all the words that we have in our vocabulary. So, some information about why we're using this function right here. First of all, we're going to use the exponential simply because we want to make everything positive. We don't want to deal with negative values here. Also, the dot product, it will be pretty much comparing or calculating the similarity between our context and our center. And when we have the u, the transpose of u times the vector of the center word, it's pretty much the dot product, but we'll pretty much just use this notation right here. Okay, and then we normalize over the entire vocabulary so we can have the actual distribution. Later on, we'll see that we do this for a batch or for a window size. And then we adjust the values or the parameters for that window size, and we keep doing this. All right? So that predictive function that we have is pretty much a softmax, and this is an example of a softmax, of course, that we take any real value, and then in the end, we're going to be having a final value between 0 and 1 here for any dimensions, and we call this a softmax, and what it actually means for us. The max here is a bit misleading because you would think you would get the max value of whatever that you have there. Is not actually the case. It simply amplifies the probability of the largest values that you have there, and soft because it will assign some probability to smaller values of whatever x that we have or that we're calculating right here, which are our word vectors. It is popular in deep learning. We don't use this exactly. It's popular pretty much to teach how it works, but in practice it's a bit more different than this. All right? And then what is the idea? After we train our model, we initialize them with some values, not relevant how we do this, so think as a random values be initialized there. And then we have to start adjusting those values in which we'll hope to get the minimum of this function that we're trying to optimize. And how we do this, you can have, you can update these values with the largest step, with a smaller step. They have their problems. We'll talk later about this also. But think as we're going to take all the parameters that we have in our function, in our optimization, in our cost function, and then the idea is, based on these initial values that we have, we're going to adjust by a factor of alpha. It's not relevant what is the value right now, and then we keep adjusting these values in a hope that we will end up with a good representation. Of course, we don't change those values randomly. We change those values in a way that last I still did not show, okay, yes, where is it? We change this in a way that we're going to minimize this objective function right here, but we'll get there. Okay. Yes, what are the parameters that we have here to work on? In our case, we compute all the vector gradients that we have there, and this data right here represents all the model parameters in one single long vector. And what are those parameters? It's pretty much the vectors for our words when it's being sent the word. Remember, V is our center word and U is our context word. Because of that, the entire dimension of parameters that we have to adjust on this, it's 2 times the dimensionality. That this is, again, arbitrary. You can select or you can set up how many dimensions you have this. Times the vocabulary, of course. And then we optimize this parameters walking down the gradient, which we'll talk later on as well. So, how we get from this, let's say, this formula here that we want, this cost function, to the actual probability, what we're observing, and what is our prediction. We'll pretty much will derive this. We will derive the gradient for the center word together. Think if you do this for the context word, it's pretty much the same thing, but the other way around. And for sake of simplicity and also make our life easier, we're going to do for one example window and one example outside word. So the idea is, let's derive this function right here and see how in the end we will direct the gradient in the direction that we want, okay? And how we do this? Well, let's first start by what we want to do. We want to maximize the function, the probability function, the likelihood function that we talked in the beginning, which is simply the product of all the probabilities that we have there, first to the window that we define, and then for the entire the entire corpus, sorry. Then we already discussed that if I want to maximize this here, it's pretty much the same thing as minimizing the negative log likelihood. So in this case, we'll alter this this j right here to the negative log probabilities, and then we're gonna minimize this function, and we already talked about all our parameters, and then we already know that to calculate the probability of this is nothing more than take the exponential between the dot product of our vectors, center and context vectors, over the sum of all those vectors combined, all right? So our idea is to first understand the direction where we have to alter this. We're gonna derive this function. How we do this, and by the way, we'll do, I guess, this example, deriving from scratch per se, and then later on when we move a bit on the matrix notation, we'll also talk about partial derivatives there, but later on we'll be more and more abstract because it's pretty much the same way, so since we know this, the other one should be trivial. So the idea is first to derive these two parts right here, so let's rewrite this to make our life easier in A and B. So by calculating the partial derivative with respect to our sent the words, if we break down this here, it's pretty much the denominator minus the numerator minus the denominator right here, and then we derive the first part and then the second part. You will see how nicely this here will be at the end. So we'll derive these two parts, and then we're going to plug this into back again to see what we have in the end. So what is the very first part that we have? So when we calculate the derivative, in this case right here, the log and the exponential, they will pretty much cancel out. So the result is not that complicated. We will end up with our context vector. So we already have the first term that we have right here. This is the actual, we'll talk later, but this is the actual observed probability that we have. And then for the second part is a bit more spiky, but then we can rewrite things. So when we calculate the partial derivative on this entire part right here, first we have to understand that we have a composition of two parts in this formula right here. The first one we can call f, and then by doing the first, the derivative of this first part, a log right here is 1 over everything that we have after that. So 1 over the sum of the exponential of the dot product of all the words that we have in our vocabulary times whatever that I had there before, the derivative of whatever that I had before there. And then to calculate the partial derivative here, we pretty much, well, before we do this, let's move this outside to make our life a bit easier. And then by doing the derivative here, it's also again two parts. First, exponential, which is somehow easy for us because we don't have to change anything. The derivative of the exponential is the actual exponential right here. And then the derivative of the second part right here, we kind of already calculated before. So in this case right here, the derivative of ux transpose vc with respect to vc, it's simply ux. Let's see if I forgot anything here. Yes, we did change the index right here simply because we have another sum. I mean, before it was w with respect to v, and now it's x with respect to the entire vocabulary, but it's pretty much the same thing. It's just a different notation. Okay, so after we calculate this, we already have the second term that we had. So it's pretty much this block right here. And now let's go back to our initial our initial cost function that we're trying to optimize and substitute things there. So let's rewrite this C with respect to A and B. And by doing that, what we have, now we have those two terms. So we have the vector of our context word right here, and then we do have the sum of the exponential of the entire vocabulary times our u of x here over the sum of this entire thing. The thing is, this looks somehow kind of similar what we saw in the previous slide, right? If we put this sum here outside, because we know we have to calculate the distribution probability over the entire vocabulary, and of course for the entire window as well, we already saw this term right here. It's pretty much what we were doing before. So if you remember, what is the probability of a context word giving its center? It's exactly what we have right here. So exponential of the dot product of context and center over the sum of this of all these vectors. And then if we rewrite this, we pretty much have this, let's say this direction where to change our parameters. So our u of O, or u of our context word right here, is the observed representation of the context word. So is the actual, let's say, is the actual value of a vector in my context word. And then this second part right here is what our model thinks the context should look like. So by having this probability and calculating this probability distribution right here, this second term times this u of x right here, it's pretty much what our model or our expectation about this, this word is. And our, let's say, our goal right here, of course, is to make sure that these two representations, one being the real world representation that we have, the vector for our context and our expectation, they will be as close as possible. It will never be zero, but we pretty much would like that to be true. And the idea is, by calculating these differences, and we'll know how we change the values in those vectors, this difference will get smaller, 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 so we know we're heading the right way because we are minimizing this cost function. But I guess that's it for now. And maybe I should say some words. Yes, of course. How much you're changing those values, because you're always going to the, let's say, the minimum of that function. You have to take care, because if you change these values too abruptly, you're going to pass the global minimum in that function, and you want to avoid that. But if you have super smaller steps or super small variations on these parameters, you will get either too long there, or you might get stuck into a local minimum, which is not what you want. Okay? Okay, so yeah, we went through the gradient for each center word V in the window, and we also need the gradients for the outside word U. So we'll do this also the other way around. We won't show how this is done. It's pretty much the same thing. And ideally, each word will compute its updates for all the parameters that are being used in that window. As I said, we will do this for the entire vocabulary, for all the words there, but you don't update these values only after you finish visiting all the words. You do this in small batches. But we'll get there as well. Yeah, okay, I had a slide about this. So, this optimization and how we're changing these values, we use something called the gradient descent, which is an algorithm to minimize the cost function that we have by changing the values that we have in this vector. For those that already took deep learning or machine learning, probably you saw this for the entire semester. This is nothing new. And then the idea is, for the current values of our parameters that we have there, we're going to calculate the gradient of our function, and then we take a small step in the direction of the negative gradient. And what that means, we will take a step in the direction with the highest slope that will lead to the minimum of our function. Okay? And how we do this? By changing the values. And if you have, let's say, a good step, you will end up on the minimum of that function that we're trying to optimize right here. But if you don't have, let's say, a larger enough step, what's going to happen is you're going to be changing the values into the direction that will get to a minimum, and by the time you start moving from this region right here in this local minimum, the cost will start increase again, so you want to avoid that, so probably going to get stuck here. There are some optimizations how to deal with this. Okay, you can do multiple runs, you can optimize using some free parameters, but hopefully we'll get there as well. Get some water. So, and how we update our values. Imagine that in order to calculate the new value, we take the old one that was what was initialized to begin with, and then we calculate the cost of that function, and then we multiply this by a given alpha there. For a single parameter, it's pretty much the same thing, but with a proper index. And all this, I would say, this last 10 minutes that we were talking about, it translates to 2 lines of code. It's just for you to have an idea what's happening behind the scenes. Of course, if you are working with optimization, this goes way beyond that, but that's not the case for us. The thing is, to calculate this for the entire vocabulary, it's quite expensive, so we don't do this, because simply in order to update our cost function for all the windows or all the vocabulary that we have or our text, it's quite expensive. So we don't want to wait a really long time before making this update. So what we do, we pretty much use the stochastic gradient descent, in which we will do these updates, but on specific windows that we have there. All right? And how we do this? It's pretty much just one extra line of code. And of course, we won't be dwelling on this. All right? The thing is, specifically for word2vec, we pretty much talk about the skipgram variable, in which we predict the context outside words given the center words. So it's exactly the example we just saw. When they proposed the algorithm, they proposed 2 versions of that, the skipgram and the continuous bag of words. The continuous bag of words is the other way around. I want to predict the center word that I have looking to the context words that I have around me. And again, the larger the context, the better will be that for you. There is a lot of debate which algorithm works better. The thing is, it really depends on the task. At least this is my personal experience with that. Depending on the task that you're using, skipgram is better. Depending on the task that you're using, continuous bag of words is better. When I was working with this closely, tasks that were related more with syntax, continuous bag of words, they did well for my scenario. And when you're doing with more semantic tasks like word sense ambiguation or document classification, the skipgram of the algorithm was a bit better, right? But you'll find all sorts of things when you're doing your research on this. There is no consensus, at least from what I found out. So this is just a representation of how these algorithms they work. So the first one, the skipgram, we want to, given the center word, we are predicting its context words, and then the continuous bag of words is the other way around. So given my context, I will predict my center word, okay? This is pretty much the initial idea of word2vec. There's a bunch of side notes, a bunch of details that we're going to go over them. Some of them is about optimization. So when we're doing the training, they don't use exactly the formula that we're talking about. They use a bit more of a complex one because it does make things way better and fast to compute. So in their training, they have 2 versions, the negative sampling and hierarchical softmax. And how do they work? Oh yeah, it's pretty much what I just said. So And we can go directly to what they do. Okay, before we get to how negative sampling works and also hierarchical softmax, another thing, they actually don't use the softmax right here. They use the sigmoid function. We will talk more about some activation functions later on in the course. But then this here will speed things for us. And later on, we'll talk more about this. It's just another way to obtain what we want here on this distribution of probabilities. But going to the negative sampling, what we do. So on top of maximizing our, let's say, probability of the real words happen there, which means that given a sentence word with the actual words that happen to appear in this context, they put something extra on this formula, in which they also sample words outside of this context window to work as a counterexample in a way that these words, they should not co-occur or they should not be part of this specific window that you have. If we change this to something that we just saw, yeah, of course. If you look in the original paper, they have this probability factor right here, in which they have an extra parameter, and these values that they have for this specific part of negative sampling, there's not much mathematical discussion about this. Simply they try with different values and they saw that this worked better. You would be surprised how many times this actually occurred on these approaches in which they were proposed, right? I'm almost sure I include the 2 original papers in the recommended literature. If you want to take a look on that, they are already there. If we change the negative sampling to something that we were working, it's pretty much we are minimizing the negative sample that we had there, which is instead of, where is it? Yes, here. So it's pretty much the same 2 vectors that we had for the context and the sentence word, but now we take something outside from that window that we had before, so nothing changed pretty much. Let's see if I forgot something here. Okay, I think that's it. On the other version of it, which is the hierarchical softmax, we do have a different representation for words, and I would like to call attention on this. You will see that as we progress with these techniques, people will come up with clever ways of representing our words simply to gain more efficiency or try to extract, let's say, more relationships between words. One thing that they come up with was to use this hierarchical softmax in which they represent the words using some sort of encoding. Here they use the Huffman encoding, which is words that appear a lot, they will have short representation, and words that don't appear that often, they will have longer codes. Oh, the other, yeah, that's correct. Later on, we'll see other kind of attempts how to represent those words using characters or subwords. I would say one of the most popular right now is using byte pair encoding, which pretty much follows the same idea as Huffman encoding, but we'll get there in about 3 or 4 lectures. All right? And I guess that's it for this. Okay. So this, I mean, word2vec, I think I talked about this in the last session. It's one of the many approaches how to come up with dense word representations. And I mean, we spent around 3 lectures on how to represent words with vector and counting co-occurrence, and then we shift to this dense representation. So instead of going through all this trouble to predict these words, why don't we use something that we already know how to do quite efficiently and try to combine with this to have a better representation? Of course, better is debatable there, but you'll see that some other approaches, and we're going to go over some of them, will make use of both things, the prediction that we just used right now and also the co-occurrence of words, okay? But we'll get there. So Another way of doing this, of course, it's global vectors or GLOVE. If you ever Google Word2Vec, probably you took a look also in GLOVE. It's pretty much on the same year as Word2Vec was proposed. I think GLOVE is 1 year later in 2014, but in any case, what is the idea behind S? In Word2Vec, we are also looking for dense representations, but we want to extract or want to unlock the potential of this co-occurrence or the counting of the co-occurrence between those words, okay? And if you remember correctly, the co-occurrence matrix, or how we count when two words co-occur, pretty much we have our entire vocabulary right here, and every time a word occurs, we simply mark the presence there. When we talk about the relationships between this co-occurrence, we didn't dig into the actual cool thing about them. So we saved this pretty much for this lecture. But before there, just a quick reminder about the co-occurrence matrix. It does have some problems, like increase in size with the vocabulary. It's really high dimensional, so you do require a lot of storage. And you might have some sparsity issues, but they come up with a clever way how to deal with this. Okay, so what is the idea behind GLOVE? Pretty much, we consider both things, let's say the best scenario from both worlds, like the count that we just saw from the past lectures and the prediction that we just saw with Word2Vec, and they try to put these things together, or they try to use at least the most interesting stuff for both of them. So on counting, we already know that's fast to train. You can use some efficient approaches in statistics. You can capture word similarity, but it does disproportionate importance to some large counts. So if you have large count of words, they will be overrepresented in your approach. Whereas on the prediction or the predict approach, they do have a better performance in most of tasks, I would say. It scales with our corpus size simply because we don't need to have this n by n matrix. It does not use statistics that well. As we saw the very first approach, how to derive Word2Vec, we saw that we don't use a very efficient way of doing this. But it's really good to capture complex patterns beyond the word similarity. So when they proposed GLOVE, they pretty much said, okay, why don't we do both with that? And okay, when you say both, it can be debatable, but the main idea behind that is they try to use the ratio of co-occurrence probabilities, and this ratio will be able to embed some implicit meaning for us. So when you're talking about the co-occurrence of those words, it's somehow interesting, but if you work with the probability of those words to occur and you do the ratio of that, you'll see that some clever properties, they emerge from this. Okay, and what are those properties per se? So when you're doing let's say the probability of a word K given the word ice, and if this K, of course, consider that you have a large corpus to calculate this, of course. If the word is related with the context word, you will end up with some higher values, and this is higher compared to this, of course, one order of magnitude. If the word is not related with the word, in this case, ice, we'll see that the values right here are really, really low. Again, if the word is somehow related, the values are higher, and when there's a word that is not necessarily the opposite, this gas is kind of the opposite of ice, but fashion is totally unrelated, you end up with those values. Okay, that's somehow interesting. Now, if we consider another context word in this case to make the co-occurrence, we see that if K is related with steam somehow, like such as in gas, we'll have a higher value than for words that steam is somehow either completely not related, such as fashion, or you can think as the opposite of that word, such as in solid. This two, let's say, this first two rows that we have in this probabilities, they are somehow informative, but not that much. Because, for example, we see that both for ice and steam, if you're trying to predict a word in this case is fashion, they have roughly the same value. So you cannot use this to differentiate much more. What they figure out is if you work with the ratio of this, which is quite nice, when the word is related with ice in this case right here, they will have higher values. So if K is related with your numerator, you'll have a higher value. When the K is related with steam, you'll have a really low value. And then if the words are either not informative or totally unrelated with that, the values pretty much, they approximate to 0. So this is pretty neat to explore, because if you have a long enough corpus, you can extract all these implicit relationships and, you know, apply in whatever task that you have. All right? So how can we capture the ratios of co-occurrence probabilities as a linear meaning components in a word vector space? If we can make the dot product, in this case right here, of the vector representation equal to the log of the co-occurrence probability in the vector difference that we have, we get the ratio of co-occurrence probabilities. So if we are able to equal this dot product with the log of the probability of these words, we can use this to calculate this ratio, which we're trying to obtain as we saw before. Of course, this is the illustrative example. How things they work behind the scene is a bit different. You do have a bunch of other components to take into account. For example, this the bias terms that you have right here. And yeah, pretty much in comparison with word2vec, our function right here is a bit different in this case, but you don't have to worry, we will not do this for now. And by doing this, and by of course also adjust the values of our vectors accordingly, we will end up with a good representation of our words according to the corpus that you are considering, of course. Taking into account this really fast overview that we just saw, can you see a potential problem with these approaches? I mean, because we saw, okay, I have one word, I have a vector representation for this word, that when the word is a context, when a word is a center word, I do the average, that's good enough to represent that. Do you see, of course, considering the static word representation that we have right now, do you see a problem with this? And I'll drink some water while you think, because my voice is fading. So, we kind of used this already in some examples. In the first class, and I guess 2 lectures ago, we have a vector representation for every single word. So, if I ask, yeah.
The meaning of the context.
That's also true. Yes? Yes, that's more technical problem, but that's true, especially if you are considering glove, this is even more problematic. Yes, that's true. If I ask you to tell me what is the meaning when I'm talking about Java as a coffee and not as a programming language, how would you pinpoint this to me in this representation? So in theory and also in practice, all the different meanings of those words, they are embedded in the dimensionality that you have for this vector. So we're talking about, we have a word, and all the times this word occur with whatever context you have, it is represented in this 50, 100, 200, 300 dimensions. Of course, the larger is the number of dimensions, the more granular will be this representation, in a sense that hopefully these dimensions, they are going to be able to capture whatever different, let's say, situations this word occurred. The thing is, this also has the problem of overrepresentation in the corpus for the meaning/context of those words, meaning that imagine that you have an entire Wikipedia. If you have more pages in the Wikipedia that talk about Java as a programming language, most likely these dimensions are able to represent Java as a programming language way better than Java as a coffee. Of course, this will be embedded there, but you will see that it's not that easy to, for example, disambiguate these words when you have just one representation for everything. Again, after we adjust all these vectors that we have for these words, these vectors are there for good. It's not like you can update those values. They're not part of, let's say, they are frozen weights, let's put it this way. Later on, we'll see techniques how we can build on top of that. In fact, most of techniques today, they take care of this because they take the context into account, and they update the values of a word based on the context at inference time. As for right now, we're not doing this, but we'll get there. Yes, so we'll also talk about some early approaches how to deal with this, and between, I would say, 2014, 15 until 2017, 18, there was a lot of approaches how to deal with this multi-sense disambiguation or multi-sense word embeddings. There's tons of techniques on this. But before we get into this, some summary about word2vec and GloVe. For word, we're talking about mainly a predictive-based model. We do have a low memory usage because we just pretty much have 2 vectors for the, let's say, for the dimensions that we arbitrarily chose for the entire vocabulary. We are able to capture some relationships, not all of them, and we also have that training via softmax is simply not feasible, so we have some other approaches here. We'll talk about the improvement of word2vec using fast text, but in about 2 lectures from now. On the other hand, we have GloVe, which is a count-based model, has high memory usage, is good to capture analogies, not that much on semantic relationships, has straightforward training. It is faster to train, but it requires a lot of memory because of the concurrency matrix that they use. And I guess that's it for the summary on this. Oh yeah, some takeaways. Both techniques and a bunch of that are built on top of them, they do require, and they were originally trained on a large training corpus, and specific corpus, they might produce better results depending on the task that you're tackling. So they do have pre-trained word embeddings in X billion of words. If you're working with a general task, that might help, but if you have a very specific case, let's say you're trying to work with document similarity on papers in biology, most likely this pre-trained word embeddings, they won't help you a thing. So you most likely either will look for something more specific. Probably you will find some already pre-trained word embeddings because we're talking stuff from the last 10 years. So there's a lot of people that pre-train a bunch of these models, all right? Data cleaning does improve your embeddings, so if you get rid of stop words, it also makes your life a bit easier, simply because those techniques, they don't take into account when you're in the context. It's not that relevant, for example, if you have a bunch of articles or pronouns, it's not that relevant for this specific use. So if you can get rid of those, it will help out. They do have similar embeddings, they do have similar results in NLP downstream tasks, and both, of course, as a problem, we saw that embed all word senses in one single word vector, and we'll hopefully see an approach how to tackle this. Before we get into this, we'll talk about pretty much 2 or 3 tasks and some evaluation metrics that we use. Yes?
One question regarding GloVe and word2vec. For example, we have the example and if we pass in a word, would that have the same word embeddings for both the cases?
No, they have different because they are initialized different, they are calculated different, they have some other free parameters. In the end, the values, they will be different. Some of them, they might be closer, but at least when I use for word sense ambiguation, document classification, word relatedness, and similarity, they had pretty much different values. At that time, I had a lot of trouble to work with GloVe simply because it required a lot of memory. Word2Vec was a bit efficient, but I found papers saying completely the opposite. They were able to work with Glove as well. Later, when we talk about an improvement on Word2Vec, more specifically paragraph vectors or doc2Vec, you see that a bunch of these techniques, especially when they were proposed, is not that clear about some, let's say, technical decisions that they had. So it's extremely hard to replicate, for example, the exact same values and vectors that they had. But we'll see an example on this.
Another question. So you mentioned about parallel to way. So for example, my initial training was based on single sentence, and when I try to, let's say, a query comes in which has a paragraph, so the training set is not same as what I'm trying to predict. Would it work efficiently on that? Would you guys work out?
But you're trying to predict the vector for an entire sentence, or?
Like my training set is based on sentences, but I'm trying something this time with a paragraph. So would the performance be same or would the should be different?
So more technically speaking, when you're doing the training with these approaches, you're, let's say, you're taking care of the text as one single string. So you're going to parse this entire thing. It doesn't matter if you have sentences or not. You are processing this entire thing. One thing that you might have to consider is how large your window will be to take care that when you're doing this running window, you won't have those weird sentences. Let's say a sentence A and a sentence B. If you put this in one single input, your window might overlap two sentences. But it really depends on how you do the entire vocabulary processing. When I did that, and I think most approaches they do this, they consider simply this as a bag of words. So they put all the text there and it processes the entire thing. Later on, we'll see some techniques how to deal with this representation, for example, a sentence or paragraphs. And we'll see that there is a vector, there's a technique that you can have an extra vector in this running window that will capture the meaning of a sentence or a paragraph that you have. But it comes with some extra computation on this, okay? Yes?
When we suppose just get the embedding vectors from them, is that useful or just redundant?
For what exactly? For the sentence? For represent the sentence of vector?
Represent the word, for example, use
Uh-huh. Okay, I see. You're talking about having like an ensemble approach in which you calculate those things separately and you concatenate them. I don't know. I mean, it might be a bit redundant in a way that you will have a representation for those words separately. If they capture whatever different aspects, it might be interesting. I don't remember any work doing this per se. Let's say you have this separate vector representation and you concatenate them together simply because it would be better, I think, to have a higher dimensionality in a hope that you capture more relationships in a granular level than doing this in a limited granular level and put them together. But this is my first assessment on this. Okay? So let's move on to some tasks and evaluation. I think we briefly mentioned this when we were testing these approaches. There are two ways pretty much of doing this. Intrinsic evaluation and extrinsic one. On the intrinsic evaluation, we have a subtask which is not that expensive to train, for example, the quality of our word vectors, or to check the quality of our language model, and etc. But ideally, we want our approaches or our models to be better on the actual extrinsic evaluation, which is the real task per se. Document classification, word disambiguation, sentiment analysis, and so on. Of course, it takes quite some time to compute depending on the approach that you're using. And of course, if, let's say, your solution is part of a bigger system, it's kind of hard to pinpoint exactly problems or contributions of this specific component over the entire solution. But just this is a quick overview on this. We will talk about two tasks today. I think I mentioned this in the very first or the second lecture. We'll go over some tasks to motivate. We'll talk today about word similarity and also document classification. On word similarity, how similar or dissimilar two words are with and without context. Because when we talk about, hey, these are two words, how close they are. Most likely, you won't be doing this with single words unless you are in a very specific Kaggle competition, Kaggle between quotes here. But most likely you were trying to see how a word given a context is similar to another. And more of the complex tasks, they go into this direction, and this is pretty much more useful for us. And document classification, we can pretty much extrapolate this for a bunch of different tasks like sentiment analysis, product reveal, social media name intent recognition, language detection. All of this in the end is classification. And so we'll take a look on even some data sets that we have available. All right, about how we evaluate this. So there are some golden data sets in which people agree on a certain score on how words were related or not. And the idea is you're going to take this pair of words, you're going to calculate whatever, let's say, similarity measure that you have. Most likely you're going to be using cosine similarity, but as we saw, there are others. And then you're going to see what is the correlation between the pair of values and score that you have with the gold standard that was provided. Popular metrics to do this, the Spearman correlation value and the Pearson correlation value. They're pretty much similar. The first one, it considers the, let's say, the ranked, I think, yes, is the ranked vector variables for whatever, let's say, two words that you are considering. Let's say two comparisons that you're doing from the gold standard with your own predictions. Yeah, so we do use cosine similarity when there is one vector per word, and this is somehow trivial, but now if we consider what we know about how we calculate the cosine similarity, which is the vector representation for that word, and we know that we use a vector to represent that, and we do the dot product with another word, we can say how much they're similar. But now, how we do this if we have multiple representations to deal with that? How would you account for this? Early approaches on how to deal with this, they were published around 2010, 2012, but this got more strength a bit after. And it is quite interesting because approaches how to deal with word with multiple senses in a vector representation, they were already thought before, let's say, this technique that we just saw that represent them using one vector, such as word2vec and glove. So how we deal with multi-sense embeddings, assuming that you have more than one vector representation for a single word. One approach how to calculate the similarity, you can use the average similarity, in which you calculate the dot product between all the possible senses or all the possible vector representations for those for this pair, and then you just average. Or after you calculate all the similarity between all the possible senses, you keep with the max value, and this we call max similarity. The thing is, on top of this average similarity for multi-sense embeddings or multi-sense word embeddings and the max one, these are considered just the pair of words. But on top of that, depending on the task or the problem that you're approaching, you also have the context, because they will provide to you, this is the word that I have, this is the context, and this another word and context, how you would relate that. So ideally, you want to consider the context to calculate how similar those two words are. And one way to deal with this is using average similarity, consider the context, which it's pretty much what we had before for we average all the senses that we have there, but also we calculate the similarity of a word sense according to the context that is provided. And it's pretty much the same thing, but when we're working with max similarity, we just take the max, the argmax of this entire computation. don't worry too much about this. This is just to give you some perspective. Let's say if you have a task or if you have a problem in which you have context into consideration, multiple representation, at least you know where to start and where to look on, all right? About some data sets. You will see that data sets, it's really tricky because everyone loves to use them. Nobody likes to propose them, simply because it's a hell lot of a work to do, especially if you want to do a high quality. And before, people would just, yeah, here's some 65 word pairs and this is how they are similar between them. Today, this doesn't fly. If you try to propose something like this, people are really more, let's say, demanding. So that being said, you would be surprised how things, at least in static word embeddings, they're still comparable. They're still tested using benchmarks that were done, I don't know how many years ago, like 30, 40 years ago, which in my opinion is not optimal, but it's a way of having a benchmark. So of course, this is not an extensive list. Most of the data sets, they are just with word pairs. So we have RG65 with 60 noun pairs. MC28 is a subset of the first one. We have WordSim 353, which was really, really popular. It's a concatenation of two different and overlapping data sets in which you are working with relatedness and similarity. They do have their own definition of that. MEN dataset, MEN 3000, it's actually called 3,000 word pairs that occur at least 700 times into these two resources that we have, UKWAC and Wikipedia. And this word also had to appear at least 50 times in this SP Game 2012. Some more complex data sets. There's SimLex 999, which is composed of nouns, verbs, adjectives. There's also YP, what's the name of this? YP 350, I don't remember, and SimVerb 3500, which are more focused on verbs. This is just to pinpoint to you, and we'll see the summary of this in about one slide. How is the composition of this data sets? Of all of this, there is one that I like. It's the Stanford Context Word Similarity data set, in which it provides a bunch of word pairs with the part of speech tagging of that word and some context in which that word fits. So it pretty much helps you to harvest some knowledge about those words. How do they look like? And I think I mentioned this in one of the classes. Most of data sets working with word disambiguation or word similarity, they focus a lot on nouns. If you're working something not on this, it's a bit more complicated to deal. And again, think that we're talking about some years ago. Now things are a bit different. You have other benchmarking such as glue, superglue, squad 1, 2, and so on. Okay? Just to give you an idea how these data sets they actually are proposed. Imagine that in this case for RG65 you have literally two lists of words and then you have the similarity of them. And depending on the data set, they will tell you exactly how these values they were computed between, sometimes in a scale between 0 and 1, 0 and 4, -2 and 2. It doesn't matter. They all somehow agree into whatever score that put two words close together or far apart. Some of these data sets, they do have, I would say, a really detailed agreement score in a way that many people look at this and human annotators, I don't know, 10 people, they look at that and said, yeah, this is our, let's say, prediction or how we think those words are similar, and then we average everything and we propose. Some of them, they are as low quality as two people annotated, and there is not even agreement between them. Just take care, especially if you're, and why we're saying this and why I'm presenting those data sets, in which some of them I like and some I don't, because depending on the technique that you're proposing, it might not generalize that well. Let's say you do your entire analysis, your entire system based on 1 or 2 data sets which are already known for having problems. So it won't generalize well, and people will point that out, okay? Just to make a comparison between, for example, the first one right here, and then Stanford one, you see how far apart they are in terms of quality or the difficulty to deal with the problem. And the word similarity, considering the Stanford context word similarity data set, you have 2 words, in this case, Brazil and nut. You do have the part of speech for these words, and then you have a text and which provides the context of that word, and the word itself is tagged. So the first word is tagged right here, and then the second part of the text, the same thing, and is also tagged, and then it's followed by the average score that you have between those 2 words, considering the context, and the other values are simply, let's say, whatever score the annotators they come up with. All right, and I'm almost sure the first one is an average. I would double check that, but in any case, document classification task. So I think the very first question to us is, okay, we saw how to represent words. How do we do this with documents? The thing is, there's a bunch of techniques how to do this. Some people, they average all the vectors equally. Some people concatenate the vectors and then they trim, because you might be thinking already, yes, if I concatenate, what happened with the documents? They have different length. They simply trim the documents for whatever coverage that they have in their data set. But yes, you are losing information with this. Some approaches, they do sum the vectors of the entire document that you have there. You will be surprised how well that works. They do consider also multi-sense embeddings. They weight the values of the words according to their location or according to the blocks in which they belong. This goes more into the aspect-based document similarity in a way that 2 documents, they are alike, but with respect to what? Which sections of the paper? So you might say that document A and document B, they are somehow related because they're close together with respect to introduction, methodology, and conclusion. And then, but this goes into a different direction. What is a good baseline to average the vectors that you have for your document representation? I would say this is the very first baseline, I would think. And how, I mean, not going to neural networks yet, how we use these features, because the words are the features of our documents or our sentence or paragraphs, how we deal with that. Most likely, you're going to be plugged into a machine learning algorithm, and then you're going to be comparing which one gives you the best result according to whatever parameters that you look into that. We will not go over this, especially because nowadays people do a bit different. We are using other architectures to take care of this, more specifically neural networks, and we'll be talking about them in the next classes. The good thing about this here, I mean, you can also do this in neural networks, but what people did also in the past, and on top of this handcrafted features, which are the words and the vectors that we have representing them, they would also put other engineered features, like, I don't know, the occurrences of some sentiment words or some presence or absence of specific keywords and so on. So on top of the word embedding that you would have, people would plug on that representation other features. Nowadays, people don't do that much. They go in a different direction. They change the training approach or the prompting approach, but we'll get there eventually. All right? Yeah, this is just a representation how we want this to occur. So we want to move from a very messy representation to a more specific one. We didn't mention that much yet, but there's also document classification tasks in which you won't have this, let's say, discrete class for each document. Sometimes documents, they belong to different categories and they are overlapping. So this is also somehow troublesome. Some data sets on document classification. ones that are really worth to mention. The first one is worth to mention because of the amount of classes that they have. The others, they have a low number of classes. This one has 23, and it's based on medical scientific paper abstracts. If you want to go into more on the classification using scientific papers, there is a data set based on archive, which is pretty advanced. They use the categories on archive as label, but it's somehow higher level. But it's a really good data set if you want to work with that. The Psi genes or Psi cluster, they are specific on the biology domain. Reuters and 20 News Group, they're probably one of the most famous data sets people used to use, especially on static word embeddings. They do have a lot of problems though, because when they were proposed, they did not curate the data set that much. So you will see that some data sets, they're simply headers or subjects of emails. And there's a bunch of weird characters there. And if you consider this on whatever task you're doing, this will put whatever performance you have down. Because of that, specifically with Reuters, you will see that there's a bunch of variations in which they take care of these 90 classes. I know that I said, hey, 23 classes is cool because they are really well-curated classes. Whereas here, these 90 classes, after the 15th one, is not that useful, in my opinion. What other data sets you can use also? BBC News, Amazon Review, Yelp Reviews, AG News, and IMDb Movie Reviews also works pretty good. Okay, yeah, just to show how they look like. This is also somehow important to keep in mind if you're working in a technique for, let's say, document classification. You want to pay attention how well it generalizes between different scenarios. And this is why on the word similarity and also in document classification, I'm presenting more than one data set. It's a common mistake, especially on early master thesis or later bachelor students say, yeah, I have a really good technique. It works really good for this data set. It's a good first step. But does this generalize well among different scenarios? And don't overlook that, because if you do, either your, let's say, thesis reviewer or the reviewer from a conference paper, they will point that out, all right? And also, if your technique doesn't generalize that well, it might not be that useful, all right? Okay, some evaluation metrics. So we have accuracy, which is pretty much how close our measures are correct with respect to their true values. So we take the true positive and true negatives and we divide by all the other, let's say, classifications that we have within our task. We have precision. What proportion of the predicted positive is truly positive? So we take the true positives that we have and we divide by over the true positives and by the ones that we calculated wrongly as positive as well. Recall or sensitivity, which what proportion of the actual positives is correctly classified. So we take, again, the true positive over the true positive plus the ones that we false categorize as negative. Specificity, which is really similar to sensitivity we just talked about. Most of the tasks you see people using kind of let's say a metric that combines precision and recall, because it doesn't help, let's say in this case right here, if the proportion of predicted positive is really high but the actual positive is really low, so it's kind of these are kind of two conflicting measures in a way, at least in practice. So usually people use the F1 score. On top of F1 score, we also have F1 micro and F1 macro. If you remember, when we talk about the data sets for document classification, we have different classes, and different classes, they have different distribution of documents or labels. And when you're doing a measure, or when you're evaluating this, you want to take that into account in a way that, let's say you have a class, let's say you have 5 classes and you categorize all right in one and all the others not, but this is overrepresented. So it doesn't help that much. You want to do good either on average, or you want to take into consideration the weight of those classes, so you can normalize the metrics. There's also, but this is just variation of F1 score. There's also F1 score with this free parameter right here, in which you can control how much importance you want to give to either precision or recall. What happened in practice? People report F1 score, at least on most NLP tasks. If you're dealing with multi-class, multi-label classification, it's a really good idea to also calculate the micro and macro F1 score, even if it doesn't fit your original work, put it in an appendix, because at least it will show that you are aware of the class distribution, which is rather important. This we can skip. And I will speed up things a bit. And just one thing, I do want to finish this. I might go over 2-3 minutes, so I ask for your patience. So when we're doing with precision and recall, ideally, we would like to have something like this here. In practice, what happened is something like this. As precision and recall, they will be kind of conflicting whatever you're doing, but let's go there. Word sense disambiguation, it's also another task that deals with word similarity or relatedness. It's probably one of the first tasks in computer science. So this is just a phrase from Professor Warren, in which said, the obvious fact that a multiplicity of languages impedes cultural interchange between the peoples of Earth and its serious deterrent, and it is a serious deterrent to international understanding, which is, I think, a quite neat sentence. We already talked about what is word sense ambiguation. So if you have one sentence in which you want to understand exactly what is the meaning of that word, probably you have to rely on some approaches to do this. In this case right here, you have to try Java. It is so good. Which one you're talking about, the programming language, the island, or coffee? And this is just to illustrate, this Java is a simple example, but we do have other scenarios in which this happened. Hopefully you can see this by these examples. The fisherman jumped off the bank into the water, so bank has a meaning. The bank down the street was robbed is another meaning, and so on and so forth. And how people deal with this problem, since it's such an old one, such as, for example, language modeling, people are been working on this for quite some time, is one of the fundamental tasks in NLP, together with machine translation, text summarization, and some others. Between the 70s and the 80s, and even before that, they had rule-based systems. During the 90s, they did rely on annotated text to take care of this, and most recently, starting in 2000, they do use hybrid systems, and they don't rely that much on tagged words. And where you can apply word sense ambiguation, although it is a fundamental task and seems quite theoretical, you can expand this to other domains the same way as document classification. So you can apply this into machine translation, information retrieval, question answering, knowledge acquisition, knowledge representation, sentiment analysis, and so on. Virtually any task that you would deal with different meanings of words, you can use this in your system. For those, again, already a bit ahead on class, you see that this kind of disambiguation between words, nowadays people do a bit differently. However, you might ask yourself, so why we're taking a look on this? Simply because this is a fundamental block and also still works quite well. Even the approach with static word embeddings. I mean, look at TF-IDF. People still use this. It has its value. So it's not like every single problem you're going to say, yes, deep learning to the core. It doesn't work like this. It's not everything is a nail, right? This usually happens with people focusing a lot on machine learning, but in any case, we'll get there. So, word sense ambiguation approach mostly are divided in data-driven, knowledge-based driven, and hybrid approaches. Data-driven, they're pretty much supervised because you do require some kind of a label text or bag of words that will allow you to identify a specific meaning of a word. This can be done either by a lexical database or some manual corpus annotated in which you train a classifier that, and then you apply for whatever scenario that you have. And how does it look like? Imagine that we have two sentences. The bank has a lot of money, debt, and stocks. The bank is in a nice green area close to water. How they would do this using a bag of word context approach. If the word that you're trying to disambiguate appear with some other keywords, you have the tag for that ambiguous word, in this case, bank. So in the first example, we were talking about a financial bag of words between money, debit, and stocks. And then the second one, we were talking about a river bank bag. Another way, you have data-driven approaches. They also rely on annotated corpus such as this, which the word is already annotated, and if you have enough examples of that and you normalize things, text in a way, you can get away with this pretty good, or you could. I will skip this because we won't have time. So, many supervised machine learning algorithms have been applied to word sense disambiguation. Yes, they do work quite well. There are a bunch of other features that we're not talking yet. So for example, the co-occurrence of words, the collocations, bigrams, part of speech, all of this can be used as a feature signal for whatever classifier you have. Yes?
I just had a question. And my question was like, if there is something that could have like different meanings, like this bank also, or could be translated into different words into another language, but there is no context really given, or also the utterance was made like intending, how do you say this, intending ambiguity. Like, what does machine translation then do? Like, if there would be a sentence, just something about the bank, and you can say this, okay, the bank is in a nice area or so, but I think it doesn't like can't be discarded that it's a bank building or something like.
Okay, so
and there is no other phrase like I guess. I mean, maybe it's a weird question, but how?
I want to see if I understand correctly. You're saying that what happens with word sense ambiguation when you, in a scenario of translation, that you move from one language to another, but because of the translation, you're going to lose some information and you might not have enough context or resources to fix that. To begin with, the quality will drop, as simple as this. Problems will arise. If you're working with low resource languages, I'm not that familiar with machine translation low resource language. They did rely a lot on, let's say, alignment of text for language that you have resources. For example, Wikipedia text you have in different language, they use this as a proxy. For some languages, this is not actually doable. So I would guess simply the quality, it would not be that good. You would lose information, of course. What you can do is, if you have, let's say, enough text from the other language, you might train a classifier to adjust the words during the translation, but yeah. Okay? You don't seem that satisfied.
Like if you have like a phrase like, for example, in English, I'm reading a tissue paper about one of what was like lay conta or whatever. And I just wondered like usually this happens, but there is not even a hint that the translation could be like entirely wrong, you know? Like,
Well, it depends if you're, let's say, if you're working in a specific downstream task and where you have the data to play around with this, or if you are in a real world scenario. If you are in a real world scenario, what happens is, usually most models, they don't rely on simply one approach. They are an ensemble of approaches, and they try to cope with the deficiencies one from another, or even use, and it might not sound that right, but for example, they use the Bible to have a very simple word representation of whatever language that you have, simply because the Bible was translated in so many different idioms that at least you have something. It won't be perfect, the translation, of course, but they use this as a proxy. And of course, if you don't have enough resources, the translation won't be that good, and ambiguity will rise. There are some specific things in NLP that are really, really, really hard to tackle. For example, sarcasm. To deal with this in NLP is a nightmare. Depending, I guess, if you're such a low resource language on NLP, that might also be problematic. But we can discuss more on this offline after the session, okay? Knowledge-based, coming back to word disambiguation using knowledge-based driven, we already talked about which resources you can explore to differentiate one word with another, and some lexical databases that you can use to do this as WordNet, ConceptNet, and LabelNet. How to use lexical database to cope with that? Pretty much you have two large groups of approaches. The first one, you use the most used sense or the most frequent sense for that word. Of course, you're limited with whatever is organized there. It does work quite well. The other group, they categorize between algorithms that are divided in path-based, information content-based, and hybrid, in which they explore the features of those lexical databases to come up with a metric that will tell you how far apart or how close apart two terms or two group of terms are. One of them, Palmer, it takes into consideration, let's use for the sake of illustration for the next slides, the representation that we have in WordNet. So it takes the depth between the lowest common subsummer, LCS here, which is, remember when we talk about hyponyms and hypernyms, think as the first hypernym between two words. So it takes into consideration the distance between the root and that lowest common hypernym between them, and also the length with respect to the root, the length of that term and the depth in that structure, and you have a similarity for that. Other approaches, they use information content to calculate that, using the information that you have in this lexical databases, and I'm skimming this very fast, simply because all these metrics, they are already implemented. You don't have to worry that much. But keep in mind that most of them are divided into actually path metrics, in which they will traverse the entire structure that you have for whatever lexical database that you have. Others, they will use information content, so they will calculate the entropy of whatever term that you have there. Other approaches, they will be based on features not bounded to a specific lexical database. Whatever those features are, it is not relevant. If you have the occurrence of, let's say, words in a text, or if you have the length of that word, or how many vowels it has, it simply doesn't matter. They use arbitrary features to calculate how two senses or two word senses they are. Then you have some hybrid approaches, which pretty much combine the structure that you have in these databases with information content, also with some arbitrary features that in any case. Of all those metrics, I would say LASK is pretty famous because you have LASK, simplified LASK, improved LASK, LASK Plus. They have a bunch of other techniques that were built upon. And the idea is to retrieve all sense definitions of words to be disambiguated from an external resource. And you take a look on how much the definition of that word overlaps with the context that you have in hand. So I take a word, for example, in WordNet, I take a look on how much this gloss definition of that word overlaps with whatever context that I have. And of course, you can build on top of this, applying multi-sense word embeddings, or you can apply, I don't know, other approaches on top of this as well. We'll see one of them, in fact. This is just the original. No, that's the simplified one, sorry. That's the simplified version. And again, all of this, they are implemented in NLTK, so you don't have to worry that much. It's not an extensive list. It's just to give you a hint if you're working with word sense ambiguation, which metrics you can use to calculate how things are similar or not. The thing is, especially, after, I don't know, 2016 or 15 per se, you will see a lot of approaches using complex systems to take care of them. They will combine word embeddings with some path-based metrics, and they will combine this with some lexical databases, and they will come up with clever ways to end up with different word representations. One of them is multi-sense embeddings through a word sense ambiguation process from 2019. Yes, that was me a long time ago. And then how we call our technique. It's called most suitable sense annotation, in a way that when we propose this idea, we want to use unlabeled words or the text itself to come up with a better way to identify the word meanings into a context without relying on so much annotated data. All right? And how we do this, we produce multi-sense embeddings, and then can be extended to any word embeddings existent. So we would provide a multi-sense representation of words, either using FastText, GloVe, Doc2Vec, or whatever representation that gives you one vector for word. We could expand that into a multi-sense representation. Okay. Another cool thing is it's a recurrent approach, so if you keep doing the algorithm over and over again, it kind of converges, so which is pretty neat. It is expensive to run though. And how does it work? Imagine that we have a running text and we have a sliding window of 3 words, and then we want to identify what is the meaning of one specific word. And again, not only you can use any word embedding to take care of this, you can also use any lexical database to take care of that, to identify which word sense you would pick. So we take the sync sets of every word. You can use BabelNet or ConceptNet or WordNet and any other net that you can find. And then we, without knowing exactly what are the labels of this word right here, we take a look on the context of that word or the gloss definition. And then in this case right here, we would say, okay, round object that is hit or thrown, kicked in games, a solid projectile that is shot by a musket, a lavish dance requiring a formal attire. So you can pretty much identify that here we're talking about ball, the second one, honey, and the third one, I think I remember, is somehow, it's coffee or so. And what is the idea that we come up with that? So we take the vector representation of the entire gloss by averaging the pre-trained word embeddings that were already calculated, so using Word2Vec, for example. By average this entire thing, we will have a vector representation for this sentence, and how do we identify which sense belongs to the center word? Pretty much, we compare all the possible, let's say, all the possible vector representation, and we do the dot product between all the senses among themselves, and hopefully the one with the highest value will be the center word that approximates the most according to its context. Here we're talking about a context word of 3, but you can expand this to whatever number you want. Hopefully, the larger is this window, you'll be able to, without any close supervision, so it's semi-supervised in this sense, we can already start dropping even the senses that do not occur at all in our training corpus. And the idea is, after we do this, the first iteration, let's say we already know that a specific word right here will take for this W3 here. After comparing all the glosses, the vector representation of the glosses among its context window, we will end up with the one that maximizes the similarity among them and the context, okay? And after you do this for the first iteration, you can rerun the same algorithm over and over again, and ideally, you will be dropping, let's say the words that are pretty much, or the word senses that are not that relevant for your corpus, all right? That being said, we can close up for today, and we'll talk again next class, all right?